by Sungyong Siu. And the title of the talk is Graph Networks with Physics-Aware Knowledge Informed in Latent Space. Sungyong, do you want to just take it away?
Okay, thank you for the introduction, and thank you for giving me such a great opportunity and attending my presentation today. So my name is Sungyong Seo, and I'm a final year computer science PhD student at USC. I'm very excited to present my research work for the graph networks with physics-aware knowledge informed in latent space. So when I started machine learning and deep learning research, I was told that there are three main features that promote deep learning to become hot. First is big data availability. As crowdsourcing is more popular, it is much easier to collect a large amount of labeled data on purpose. Furthermore, as sensor techniques such as wearable sensors are also highly developed, it is readily accessible to collect data which have been considered as expensive dataset previously. And second, new machine learning neural network techniques. As enough data samples are available, it is possible to train more complicated models, such as transformer, graph networks, residual networks without overfitting. Finally, a lot faster computing resources, such as GPU and tensor processing unit, enable to reduce training time significantly and make everything in realistic setting. Main assumption behind data-driven learning is that all we need to train a model are in dataset explicitly or implicitly, and they can be extracted or learned during training. It is a bit surprising assumption for me at the very beginning of my PhD, since it means that we can simply ignore any features developed by domain expert, and what we only need to do is just feeding data to a model as many as possible. In fact, this assumption works very well over many applications in computer vision and natural language processing. However, I had a lot of questions about the omnipotence of data and keep asking to myself one fundamental question: do data always efficiently tell everything to train a model? There are some challenges in practice if we only dependent on data, especially when there is some knowledge which is not very easily learnable from data itself. So it is hard to learn necessary features which are not given by explicit labels. For example, when we model physical dynamics by simply feeding current and next state as input and output pair to neural networks, the neural networks can easily learn a mapping relation from the current state to next state. However, it is hard to learn implicit rules or constraints such as energy or momentum conservation. Therefore, output of a model can violate must follow rules or constraint, and it causes less robust model behavior. By providing necessary rules explicitly, we can find better optimized weight, which provide not only lower error, but also trustable output. So we conduct a simple learning task from synthetic dataset from double pendulum dynamics. First, we generate a sequence of angular displacement and velocities of two connected objects with damping coefficient. Then we feed a state vector at time t to deep neural network, and runnable parameters in the networks are trained by supervised loss defined on between a prediction and the ground truth of next state vector. Once model is trained, we could see that the prediction error is significantly small. As the left figure shows, the prediction and ground truth are very close, and it implies that a model is able to learn a relation between the current and next state. However, when we plot the energy curve from the predicted state, we could see that a number of predictions actually violate the energy conservation law. As non-zero damping coefficient exists, the energy should be monotonically decreased as time goes by, but the right figure shows that the predicted energy, which is green curve, is actually up and down. This example clearly shows that the data-driven approach is not perfect, and it may miss important constraints if they are not explicitly provided. Then why do we propose physics-aware models? First, as sensor-based data get more popular, It is easy to collect observations for natural phenomena such as climate, air, and sea surface data. Many physicists and computer scientists are interested in modeling physical systems in a different methodology, such as data-driven learning these days. Second, for the spatio-temporal observations from physical systems, there are explicit rules, knowledge, or constraints from physics, which are beneficial for learning the models, so that we can get benefits by incorporating the empirical knowledge for data-driven models. In this work, we are interested in modeling this kind of physics phenomena. It is governed by some physical process happening in a continuous space, but we only have a limited number of irregularly distributed observations of it. For example, temperature, rainfall, and wind speed are governed by the rules of physics or atmosphere, which are defined on continuous space, the space of the Earth. However, we usually only have access to the records collected by the weather stations, which are sparse and irregularly spaced, not aligned to any grid. As a result, we get a set of signals at observed point. Since the signals are not mutually independent but correlated to each other, especially among signals spatially closely located, therefore we can introduce a graph structure to provide the structural information. Modeling this kind of data requires us to consider two important aspects: physics-aware modeling and relational learning. Here is our problem formulation. We have a sequence of sensor-based spatio-temporal observations, and the observations are governed by a set of physics-based equations. While the exact equation is unknown, we have physics-based knowledge such as a subset of the exact equation. For example, it is very difficult to derive the exact equation describing temperature dynamics. We have known that the quantity is following a simpler equation such as the diffusion equation or diffusion convection equation. Then we present a method to incorporate the domain knowledge given as a form of partial differential equations with a data-driven model trained on sparse observations from sensors. So given the simpler equation, we provide an inductive bias to a data-driven model, and we are going to fill the gap between the known and unknown equations by learning parameters from sensor-based observations. So before going into the main idea, I would like to briefly recap background for my works. As observations are from discretely distributed sensors, it is hard to apply existing techniques defined on continuous or dense data, such as regular convolutional layers. Instead, we can define the data on a graph, which is defined by a set of vertices, edges, and weight metrics. Recently, graph networks, which are counterpart of convolutional neural networks in dense features, are introduced. It generalizes relations among vertices, edges, and a whole graph. By aggregating neighboring information for an edge and a node, we can propagate information between themselves as well as update their latent representations as well. As we saw in the previous slide, graph networks provide combinatorial generalization, and they handle entities and relations which correspond positional features and directional features in physics. In continuous space, we can define scalar and vector field. The concept can be transferred to node and edge features, respectively, on a graph. For example, a signal at a certain coordinate can be interpreted as a node value, and relational information between 2 points, such as a gradient, can be interpreted as an edge value. Based on node and edge values, we can define discrete operators on graphs. Gradient can be understood as a function mapping from a node values to an edge value, And divergence is a function aggregating a set of edge values to a single node value. And Laplacian is a second-order spatial derivative, and it is a node-to-node function defined in this way. In other words, we can seamlessly define core spatial derivatives in PDEs on a discrete space, such as graph. In general, graph networks can be regarded as a module that updates a graph state, including attributes of node, edge, and a whole graph. This property can be applicable to physics equations, which consist of positional and directional values. Therefore, here the G prime here is considered as a next state of a graph signal. Then we can define a constraint between G and G prime based on our knowledge. For example, if we are aware that a static equation such as Laplace equation is important to understand the given observation, we impose the equation between the current node values and the next node values. This idea can be applicable to dynamic equations as well. For example, if we have knowledge that the diffusion equation is essential for graph signals, we can impose corresponding constraint between G and G prime. One challenge to impose such a constraint to a model is that it is usually hard to predefine the unknown coefficient in the constraint. For example, while we have knowledge that the input signal has a wave property, the speed of waves is usually unknown. It will be even worse when multiple input signals are involved, since each signal is governed by different parameters in the same kind of equation. To address this issue, we can transform the input signals to latent space first and use a single equation in the latent space instead of imposing multiple equations to input signals separately. So we first apply an encoder to transform a set of attributes of nodes and edges into latent space. Then we update the graph state sequentially in the latent space and impose a domain-based knowledge in the latent space. Finally, the sequentially updated attributes are retransformed to the original space by a decoder. So this is the proposed idea, so-called physics-aware graph networks. So the blue blocks have the learnable parameters, and the orange blocks are objective functions in our model. And then this operator is a concatenation. The objective function L consists of two parts, the supervised loss and physics-based loss. For the regression task, this supervised loss can be defined as a mean squared error, and then physics-based loss is defined as we discussed in the previous slide. So, for example, if we have knowledge that these observations can be partially described by the diffusion equation, we can define this physics-based loss function in this way. This physics-based loss can be also regarded as a self-supervised objective based on our domain knowledge. Here is dataset and experimental result. We collected hourly recorded climate observations across the Southern California regions, Los Angeles and San Diego, over 16 days. In each region, we have 10 different spatial temporal observations on each sensor. We first build a graph based on sensors' location information from KNN algorithm, and then we train a proposed model as well as other baselines for one-step prediction task. In this table, we can find that baselines do not consider spatial temporal structure such as MLP and LSTM are significantly outperformed by other models leveraging the structure. That is, knowing spatially neighboring information is helpful. We also find that PAGN, the proposed model with the diffusion equation, provides the least error as well as the standard deviation. It implies that the diffusive property provides a strong inductive bias, and the smaller standard deviation also tells us that the optimization process is more stable. We also evaluate the effectiveness of the state-wise regularization more carefully. So we conducted the multiple-step prediction task. For this task, the recurrent modules are modified to predict input observations as well, and the predict one is refed into the model for future time steps. So while the models having a recurrent modules are able to predict a few more steps reasonably, there are a couple of things we should pay attention. So first, the result imply that utilizing neighboring information is important because a GN-only model shows a similar or better MSE compared to the LSTM, even though it has a simple recurrent module that is not as good as that of the LSTM. Second, we found that the diffusion equation in PAGN gives the stable state transition, and the property provides slowly varying latent state, which are described particularly for the climate forecasting. And one of the benefits of physics-aware learning is the data efficiency. We explore how much the physics constraint is helpful by testing if PAGN can be well trained when the number of data for the supervised objective is limited. So we randomly sampled the training data, which were used to optimize the total loss function, and the left unsampled data were only used to minimize the physics constraint. And we found that the diffusion equation can benefit to optimize PAGN even if the target observations are partially available. Although the overall performance of PAGN are degraded when fewer number of sampled data are used, the errors are not far deviated from the GA-only model. So to study the importance of a physics term, we trained PAGN with different lambda controlling the importance of the physics term. While the physics term is helpful, we found that the term is not supposed to be dominant according to this figure. This is intuitive since the term only provides partial knowledge, which changes the loss surface to help parameters more stable to predict the next signals instead of governing the dynamics explicitly. Finally, we verified that the effect of physics-based equation is not arbitrary or random. We uniformly sample coefficient from a certain distribution and apply it to the model. This table shows that the random equation significantly degrades the overall prediction quality. Also, we apply superposed equation, the superposition of the diffusion and wave equation as the physics-based constraint. And you can see that the simple superposition of two equations does not always guarantee a lower error, even if each equation is helpful separately. When the two equations are non-linearly connected in the unknown exact equation, the superposition cannot provide meaningful inductive bias. So the result demonstrates that the physics term is unuseful inductive bias when it is properly defined. So here's the conclusion. So we developed a novel physics-aware learning architecture called PAGN, which incorporates differentiable physics equations with a graph network framework. And we explored the performance of PAGN on graph signal prediction tests to demonstrate that the physics-based inductive bias is helpful to provide a significant improvement in one-step and multi-step prediction tasks and make a model more robust. And finally, we investigate the effectiveness and the importance of PAGN from climate prediction to provide how physics knowledge can be beneficial for prediction performance. Okay, this is the last slide of my presentation.